Section 21 of The Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 2, edited by Francis Rolt Wheeler. Geology. Chapter 11, Structural Geology, Part 2. The causes of crustal deformations are very obscure, and there is much difference of opinion concerning them. When strata are buried under a sufficient depth of overlying rock, to crush them they become virtually plastic, and yield to the compressive force by bending. The movement would seem not to be a true molecular flow, but rather a gliding of the mineral particles one upon another. Geologists accordingly distinguish a shell of flowage, in which the rocks all yield plastically, a more superficial shell of fracture, in which all but the softest rocks break on compression, and between the two a shell of fracture and flowage, in which some rocks break and others bend according to their rigidity. The depth of the zone of flowage is estimated at 20,000 to 30,000 feet below the surface. One explanation made by Willis is that such phenomena are developed in regions that have been raised by upwarping above a position of adequate support, whence results a system of fractures and the settling and readjusting of the fault blocks. Quite a different type of explanation seeks to account for the phenomena of faulting by the transfers of molten magmas deep within the earth. Not only are the violent migrations of igneous material the cause of complex faulting, says J.A. Reid, but also it is most reasonable to conceive that the deeper and more gradual movements of the subcrust are the cause of the larger fault systems. Given this cause of faulting, the heretofore puzzling facts are satisfactorily and easily explained. Compression and tension still remain true causes of faulting, but mainly as local and proximate ones. The common expression tilting of fault blocks attains a deeper significance, for this tilting may be more largely the result of subcrust migrations than of mere force of gravity. Cases of horizontal motion and pivotal motion become simple, for there is no necessary unchangeable relation between the direction of the force and the position of the fracture plane. A modification of this hypothesis has been proposed by Professor Chamberlain, who regards the downward movements of segments of the Earth's crust as primary and the horizontal movements as incidental to the former. Rocks are not to be considered as unbroken solids, even the hardest and most compressed of them, for the reason that they are all interspersed with tiny crevices and sometimes larger cracks, which, as they bear a definite relation to the structure of the whole strata, are known as joints. Some of these, known as master joints, extend immense distances below ground and form a natural beginning for quarrying stone, but there are usually also minor joints as well. In igneous rocks, this is obviously due to the contraction on cooling. But there is a great deal of irregularity or unconformity, as it is usually called, in the rocks themselves, strata which have been laid down with but little interruption, which are parallel to the bedding places, and on which the movements of the Earth's crust have operated in a uniform manner, show by their structure the comparative peace in which they have lain, and are said to be conformable. But where two groups are found which have been differently acted upon by reason of having been laid down in different periods, then these two groups are not conformable with each other, and their relation is known as unconformity. Volcanoes, like all other mountains, are subject to the destructive effects of the atmosphere, rivers, and the sea. In the Pacific states may be found admirable examples of volcanic cones in various stages of erosion, notably Mount Shasta and Mount Rainier. These mountains, however, merely exemplify the earliest stages of degradation. As time goes on, the loftiest cones will be worn away, and at last only the worn down and hardly recognizable stump of the volcano remains, which is known as a volcanic neck. The neck consists of the funnel or vent filled up with the hardened lava of the last eruption. The diamond mines of South Africa are in almost cylindrical pipes, which are cut through stratified rocks and are filled with an irregular agglomerate. On the surface, the pipes show no topographical indication of their presence, but are quite level with the ground. Lava flows and sheets, which were poured out on the surface of the ground, may be recognized at a glance and traced to the vent whence they issued. Fragmental products are positive proof of volcanic action, for they cannot be formed underground. The plutonic rocks form a series which no one has ever observed in the course of formation because they were solidified at greater or less depths underground. Though these unstratified masses cannot be observed in the process of formation, as may the lavas and pyroclastic rocks, yet the nature of the rocks themselves and their relation to the volcanic and stratified rocks afford a satisfactory explanation of themselves. A primary division of the plutonic masses is into 1. Injected and 2. Subjacent bodies. An injected body, says R. Daly, is one which is entirely enclosed within the invaded formations, except along the relatively narrow openings to the chamber where the latter has been in communication with the feeding reservoir. Subjacent bodies, on the other hand, have no floor upon which the intrusive mass rests, the communication with the Earth's interior being by great openings, which enlarge downward indefinitely within the limits of observation. Injected bodies are of manifold variety of shapes and sizes, and differ in their relations to the enclosing or country rock, and different terms are accordingly used to describe them. A dike is a vertical or steeply inclined wall of igneous rock, which was forced up into a fissure when molten and there consolidated. Dikes of a certain kind may actually be seen in the making, as when the lava column of a volcano bursts its way through fissures in the cone. Intrusive veins are smaller and more irregular. Frequently branching fissures which have been filled with an igneous magma, they may only be a few inches in thickness, and may often be traced to the mass which gave them off. Sills or intrusive sheets are horizontal or moderately inclined masses of igneous rock, which have small thickness as compared with their lateral extent. Sheets conform to the bedding planes of the strata, often running long distances between the same two beds, but if they can be traced far enough, they may generally be found cutting across the strata at one point or another. In thickness, they vary from a few feet to several hundreds of feet. The Palisades of the Hudson are formed by a sheet of unusual thickness. Its outcrop is 70 miles long from north to south, and its thickness varies from 300 to 850 feet. A laccolith is a large lenticular mass of igneous rock filling a chamber which it has made for itself by lifting the overlying strata into a dome-like shape. The magma was supplied from below through a relatively small pipe or fissure. The rock of which laccoliths are made is nearly always of the highly siliceous and less fusible kinds, so that it can more easily lift the strata than force its way between them. Batholiths are great masses of plutonic rock, hundreds or even thousands of miles in extent. In general characteristics, they agree with stocks, except for their very much greater size. Granite is the commonest batholithic rock, and in such masses forms the core of many great mountain ranges like the Sierra Nevada and the Rocky Mountains. Much has been said of the manner in which rocks are cut down and built up again by the destructive agent of atmosphere and water, but there is another force which has led to the transformation of a rock from its original form, and this is known as metamorphism. The term is somewhat vague, for so many factors entering into the making of metamorphic rocks, and the process took place so many eons ago, that it is all but impossible to gain a clear conception of the manner in which they have come into being. An increase in hardness and in the degree of crystallization occurs, and not infrequently includes the generation of an entirely new set of minerals, characteristically arranged. Whether the original of the rock so metamorphosed was igneous or sedimentary cannot always be determined. Metamorphism, as classified by Scott, is of two quite distinct kinds: 1. Contact or local, and 2. Regional metamorphism. Contact metamorphism, he says, is the change effected in surrounding rocks by igneous magmas. There is a difference between the effects produced by a surface lava flow and those caused by a plutonic intrusive. In the former case, the results are usually not very striking because of the way in which a lava stream surrounds itself with non-conducting scoriae, and are such as may be referred to the action of dry heat. Bituminous coal is changed into a natural coke by the removal of its volatile constituents. Clay may be baked into a hard red rock looking like earthenware, and limestone changed to quicklime by driving off carbonic acid gas. Plutonic intrusions are more efficient agents of change because they are presumably of a higher temperature and retain their heat longer, and because the vapors and gases which they contain cannot escape into the atmosphere but strongly affect the invaded rocks. The rock invaded and metamorphosed may be either sedimentary, igneous, or already metamorphic, and the effects may be very marked or surprisingly small. Indeed, it is often quite impossible to say why the changes should be so insignificant. The distance to which the zone of change extends is wider when the intrusive mass cuts across the strata than when it follows the bedding plane, so that a dike or stock is more effective than a sill. Contact metamorphism, as its name implies, is a local phenomenon, but a widely ramifying and complex system of igneous intrusions may change large areas of sedimentary rocks. Regional or dynamic metamorphism applies to the reconstruction of rocks upon a great scale in areas covering, it may be, thousands of square miles, and evidently other processes in addition to those of contact metamorphism are needed to explain such widespread changes. Regionally, metamorphic rocks are, with the exception of the slates, thoroughly crystalline, and usually have lost all trace of whatever fossils and stratification planes they may originally have had. The first step in metamorphism consists in a mere hardening of the rock, accompanied with the loss of water and other volatile substances. In the second stage, the component minerals already present are crystallized, but new compounds are sparingly formed. The stage is frequently accompanied by cleavage, which, to distinguish it from that of minerals, is often called slaty cleavage. Cleavage, suggests C.R. Van Hise, is a capacity present in some rocks to break in certain directions more easily than in others, while fissility is a structure in some rocks by virtue of which they are already separated into parallel laminae in a state of nature. The term fissility thus complements cleavage, and the two are included under cleavage as ordinarily defined. Ordinary roofing slate is one of the best possible examples of a cleaved rock, and in beds of slate interstratified with other rocks, the cleavage is usually quite perfect in the former, absent or but partially developed in the latter. The causes of metamorphism have been summarized by W.B. Scott as follows. 1. Heat is evidently a very important factor of change, as is shown by the phenomena of contact metamorphism, and by numerous experiments by which the process has been imitated successfully. In contact metamorphism, the heat is derived from the igneous magmas, and in dynamic, it is in part mechanically generated, in part due to the interior heat of the Earth invading deeply buried masses. 2. Compression is believed to be the great agent of dynamic metamorphism, and the amount of the change depends upon the intensity of the compression and the depth at which it operates. Hence the varying results, ranging from gentle folding at one end of the series through violent folding to complete reconstruction, crystallization, and foliation at the other. 3. Moisture is another potent agent of reconstruction. Superheated water under pressure is able to attack and dissolve the most refractory substances and to build them up into new combinations. Many minerals, such as feldspars, which have never been artificially crystallized by dry heat alone, will crystallize readily in the presence of superheated water, and the water lowers the temperature necessary for metamorphism. Rocks which melt at 2,500 degrees Fahrenheit, dry heat becomes pasty at 750 degrees Fahrenheit in the presence of water. In contact metamorphism, steam is a very important factor of change, but other vapors and gases play an efficient part. 4. Pressure, as distinguished from active compression, is a necessity for any extensive metamorphic action, whether contact or dynamic. It is the difference of pressure which is responsible for the different effects of surface flows of lava and of subterranean intrusions, and which gives to depth its importance as a controlling factor. The deadweight pressure of overlying rocks prevents the rapid escape of the mineralizing vapors, and when sufficiently great, causes the rock to shear and flow without fracture. Limestone, heated at the pressure of the atmosphere in a lime kiln or an open vessel, becomes quicklime through the expulsion of carbonic acid gas. But heated under pressure so that the gas cannot escape, it crystallizes into marble. Such pressure also is an essential factor in dynamic metamorphism, as a precondition in enabling the rock to behave more or less plastically under active compression and without shattering. Dynamic metamorphism must, therefore, take place at considerable depths below the surface. The non-foliated rocks represent the less advanced stages of metamorphism in which the forces of compression may have produced cleavage or fissility, but not foliation. The fissures, veins, and faults, which are to be found alike in igneous, sedimentary, and metamorphic rocks, afford an excellent opportunity for the intrusion into the rock of matter of a dissimilar character. Thus, waters-bearing mineral compounds in solution, passing over such crevice or fissure, might readily precipitate that which it bears, each tiny grain of precipitated mineral forcing out water at the top. Sometimes these veins are filled in again with the same form of matter as that of which the main rock is composed, but different in structure. Sometimes the veins are filled by sediment which has been blown or washed in, and not infrequently fissures caused by earthquakes have been filled up from below by the intrusion of alien substances forced up by the interior pressure. Fissures thus filled vary greatly in dimensions, from a few inches to many miles in length. The minute veins are filled with material derived from the walls by solution and redeposited in the crevices, such as the veins of crystallized calcite in limestone. Great fissure veins, on the other hand, which may run unchanged for many miles and penetrate to depths beyond the reach of mining, are characterized, says Spur, by regular straight walls, by a fairly constant width, and by a definite direction of both strike and dip. A third class of mineral veins is composed of the veins of replacement, in which the circulating waters have not merely deposited minerals in an open fissure, but have gradually substituted one substance for another by dissolving out the latter and replacing it with the former. It may be molecule by molecule, so that the replacing minerals are pseudomorphs after the older series. A replacement vein represents a water channel of some kind, and so it has a more or less definite direction, but it seldom has sharply defined walls, for the new deposits impregnate the country rock and fade away into it. Replacement veins are most commonly found in limestones, since those are the most readily soluble rocks, but they also occur in rocks which are relatively very insoluble, such as sandstones, and in igneous rocks like granite. Frequently, the ores of the commercially valuable metals are found in mineral veins, which then are called metalliferous veins. Structural geology, says W. B. Scott, in summarizing up the questions relative to the formation of the rocks, brings vividly before one the innumerable changes through which the Earth's surface has passed and which are recorded in the rocks. The sedimentary rocks, originally laid down underwater in approximately horizontal positions, have been upheaved into land surfaces, either without losing that horizontality or being tilted, folded, compressed, or even violently overturned. Or they may be fractured and dislocated in great faults and thrusts. These movements have been found to be due to enormous lateral compression set up within the crust of the earth, a compression generated in some manner not yet clearly understood. Whether folding or faulting shall result from a given compression depends upon the rigidity of the strata, upon the load which overlies them, and the sudden or gradual way in which compression is applied. The results of compression on a large scale are accompanied by certain minor changes not less characteristic. Compressed rocks are cleaved, fissile, or schistose, according to the intensity of the action and whether the rocks affected are in the shell of flowage or of fracture. These changes may go so far as completely to reconstruct the minerals of the rocks, destroying the old, generating new, and obliterating the original character of the strata. Thus, displacements, dislocations, cleavage, fissility, and dynamic metamorphism are but the varying results of lateral compression acting under different conditions and at varying depths. Another class of rocks, The igneous, massive or unstratified, were found to have penetrated and overflowed the strata and to have consolidated in the fissures and cavities which they have made for themselves, or to have been poured out freely on the surface. According to the circumstances under which these masses have cooled, the resulting rock is of glassy, porphyritic, finely or coarsely crystalline texture. When solidified as sheets or dikes, the igneous rocks may be folded, faulted, cleaved, or metamorphosed like the strata, and when a region has been long and repeatedly subject to compression, its structure may become excessively complex, and the metamorphosis of its rocks so complete that not even the most careful examination will suffice to distinguish those rocks which were originally sedimentary from those which were igneous. Highly heated waters circulating through fissures and along the joint planes of the rocks deposit the substances which form the mineral and metalliferous veins, though concerning the source of these substances and of the solvent waters there is much difference of opinion. Our study has taught us that many of these processes go on deep within the Earth's crust, and hence cannot be directly observed, but must be inferred from their results. Encouraging progress has already been made in this work, but very much more remains to be done before a knowledge of structure and its full meaning shall be even approximately complete. End of section 21.